the main areas are for us. And if there are any fire drills or anything, it'll be me and Howard just to handle that with you guys. Okay. Right, so today's talk, Performance is in the Detail, by Stephen Edge, Materials and Processes in Mercedes Formula One Power Units. To tell you a little bit about the speaker, Stephen Edge. Thank you for coming here tonight. Stephen's a senior materials engineer in Mercedes High Performance Powertrains. For the last 4 years, he has combined technically advanced world of aerospace and the fast-paced world of automotive, meeting the challenges faced at Mercedes High Performance Powertrain of the champion-winning Formula One team. In addition, Stephen has also worked with Formula E team and Project One Hypercar. His work has entailed developing components, characterizing and introducing new materials. He has spent countless hours staring down at microscopes at fracture surfaces. Prior to Mercedes, Stephen has worked at JLR and Augusta Westlands, amongst other companies, as a senior metallurgist and research engineer. And Stephen has an MSc in Advanced Materials from Cranfield University and a BEng Materials Engineering from Coventry University. So thank you, Stephen, for coming here tonight, and I hand it over to you now for Performances in the Detail.
Thank you, Naaman. Very lovely words. Hang on a sec, I should just get lights up. Sure.
Second.
Here now. Apologies, that's trying to get the technology right first. Thank you very much, Naaman. Thank you for that lovely introduction. First of all, it's great to be here. It's lovely to actually see people in person. I have to say, it's been a very long time since I've done anything in person. I think it's been about 4 years since I've actually seen some faces looking back at me when I'm doing a presentation. So it's a genuine pleasure to see people here tonight. And of course, nice of people to join in as well on Teams. Before I go any further, I just want to say a big thank you to both Howard and Naaman, not just for inviting me here to talk today, but also for the hard work they put in. These events do take some putting together, organising. So yeah, a big thank you very much for the hard work you do to get these events working. Let me introduce myself. My name is Stephen Edge. I'm a materials and processing engineer at Mercedes High Performance Powertrain. So that's where we make the Formula One engines, amongst other things. And today I'm going to talk to you about the materials and processing and how the performance is in the detail. Before I go any further, see if I can move that down there slightly. Not going to move, is it?
Minimize it.
That'll do. Right, quick introduction to what I'm going to talk about tonight. So, first thing I want to talk about is sort of the development process that we have at Mercedes. Probably follows along the same sort of development routes that a lot of engineering firms would recognise. But I think we do things a little bit differently at Mercedes. I want to talk about the role that materials play in this, and as a materials engineer, how I fit into those processes. and how Mercedes actually takes some of that knowledge that we get as a materials engineer involved in those processes, and how that fits into the power units themselves. And lastly, I really want to talk about the benefits of collaboration. So when Naaman asked me to come and talk, it's really a good opportunity to work with engineers, because on a daily basis I work with engineers, I work with manufacturing, and we really see the benefits of collaboration. So hopefully we'll be able to see the benefits of collaboration. So a little bit about me. I think Naaman probably said a little bit more than I expected, so I'm just going to whiz through these. Growing up, I had two passions in my life, which are both Lego and Formula One. So that naturally ended up with being an engineer, but not a traditional engineer. Went into always had a materials and processing based career. So started off in research and development at Alcan in Banbury. Diversified into doing things like PVD coatings, so that's DLCs and titanium nitrides, developing some of the coatings like that. Worked in worked in the aerospace industry, AgustaWestland, looking at military helicopters. That's where I sort of learned a lot of the failure investigation sort of skills. And then at JLR, looking at powertrains, transmissions, and helping with the electrification side of things. Got myself an MSc in materials from Cranfield, and finally put all these skills together. They'll come together and working at Mercedes AMG high performance powertrains. I want to say a little bit about Mercedes AMG high performance powertrains. So I think it's quite important to understand the process, understand how Mercedes do things a little bit differently. So what is Mercedes high performance powertrains? Well, this is the what you can see here is a campus site. It's based up in Brixworth, not too far from here in Northamptonshire, pretty close to the Formula One team. But we make the engines, so the powertrains for the Formula One teams, and down at Brackley they'll make the chassis side of it. So it employs about 1,000 people, give or take. I think it might be a few less at the moment since COVID, but still quite a few people, near enough 1,000 people. But the main aspect of Brixworth is that they do all sorts of every aspect of the development under one roof. So we've got the engineering centre, you see at the bottom left there. Can I just check down the bottom here? That's the materials department in that centre bay, and so we really do sit right in the centre of the engineering community. And all the engineers are sort of around us. So within Brixworth, they've got the dedicated design centre. Right next door, quite literally 30 seconds walk from my desk, you can get to the manufacturing hall. And the manufacturing hall makes something like 70% of the components. So it's all machining happens next door. They've got a huge amount of capabilities, all sorts of different machines to get things turned around and manufactured quickly. And then finally, they do the testing there as well. So all the engines are tested on our dynos. We've got something like 8 dynos over at Brixworth, and that helps give us the cycle. So you got the ability to design the parts. You can then manufacture the parts, and then you can test them. What that generally often means is if something's gone not quite as you expected on the dyno, within generally a couple of days, we'll have it re-engineered, something manufactured, put back on the dyno, and it's testing within sort of a 5-day turnaround. So that's one of the key parts that helps fast-paced development is having everything under one roof and having it so accessible. We don't just do Formula One there. We're rapidly being seen by Stuttgart as part of their I suppose rapid prototyping, rapid development process. So we worked with Mercedes on the EQXX. Not sure if anybody's aware of EQXX, This was it's a record-breaking car that's actually done 1,000 kilometers on one charge. At Brixworth, we engineered the battery for that, and that was completed in a project time from 9 months from inception through to delivery of the component. We've also got very interesting projects down there. Project One, once again, a very high-end project for Mercedes Stuttgart, and that is quite literally a Formula One engine in a road car. So that was the biggest challenge we've had, is trying to take a Formula One engine, and I can say wholeheartedly it is a genuine Formula One engine in there, trying to make it road legal. So that's one of the biggest challenges we've had, and we're still going through it. But I believe we've now got some of the customers have those the cars in their hands. So it's it's a real sense of pride down there for that project as well. So we do other projects as well. It is a very much an engineering centre, but the main thing that we do is our Formula One project. This is, I suppose, the main thing to think of high performance powertrain is we are actually a supplier to the Formula One teams. So we supply the powertrain to the Mercedes Formula One team, but also the customer teams of McLaren, customer teams of Aston Martin and Williams as well. That's a little bit about what they do down there. What is it that Mercedes HPP actually make? And the reality is they make very efficient powertrains. So Mercedes engine, the current iteration of the Formula One engine, is a V6, and this is over 50% thermal efficient. The average road car at the moment is 35% efficient, so it's a much more efficient motor, a power unit, than you can get in the general road cars. And how do they do this? This is a 1.6 litre 24 valve V6, 15,000 RPM, and they have two powerful motors in there, and these really make a big difference to the power unit. First one is the MGU-H. The MGU-H is an electric motor that goes within the exhaust system, and that when the exhaust gases go through, spins a turbine that generates the electricity that goes into the battery. When the engine's not spinning so high, it then turns into a motor, and that spins the turbo to get rid of the turbo lag. So it's quite a ingenious and innovative component. The other side is the MGU-K, and that's motor generator units kinetic. So the kinetic side is because it's connected directly to the crank. So that provides another 160 horsepower worth of electric power on demand. So it's 33.3 seconds per lap. And when obviously under braking, that turns into a generator as well. That feeds energy back to the battery. And of course, the last bit, probably the bit most people forget, but one of the hardest working parts is the battery. We've got such projects like the Formula One. How do we get the better efficiency? There's things like direct injection that gives you much better combustion control. So there's some things like the MGU-H as well, the electric turbocharger. These give the much better performance out of the engine. So much so that the current 1.6 litre on its own is as powerful as the 2.4 litre V8 that it's normally aspirated, that it's took over from. And that's before you then put the 160 horsepower of the MGU-K motor on there as well. But I said the energy storage is one of the key differentiators, because unlike a normal battery, this battery has to completely charge and discharge up to 70 times in a Grand Prix. So once a lap, that has to completely discharge all its energy and then charge it back up again. So that's, imagine your phone having to charge and discharge that amount of times in sort of once a minute. takes a very different sort of technology to be able to do that. So in Formula One, the batteries and the battery packs that you see in Formula One are very different to anything you'll see in the road cars at the moment. So that's a lot about Mercedes. That's a lot about the projects and the things that we do. But the thing I really wanted to talk to you today, and is try to piece it all together, is how does a materials engineer work in this environment, and what do we actually do to improve things? Well, I'd like to think of it as we add detail to some of the engineering. So during things like the material and process selection, engineers will give us real detail on what they want, whether it is the temperatures, or whether it's a wear resistance, or whatever it is that they need, the properties that they need. They give us that detail to go into the material selection. We use the detailed engineering requirements to help drive these process selections. Then we have detailed material characterization. So modern engineering, you need an awful lot of the accurate properties to be able to do a lot of the FEA analysis. So materials engineering at the heart of that, making sure that we get very accurate material properties for the components and for the engineers to put into the simulation. And then lastly, material processes and specifications. So having done an awful lot of work doing all the characterization, you have to make sure that the properties that you get are accurately reflected in the manufacturing processes used. So we've got to make sure that's a robust manufacturing process. So quite often we are just that link with a detailed communication between the engineering teams and the manufacturing teams. So this is where we add the value to be able to try and take the engineers' brilliant ideas and try and make them into reality for the manufacturers to actually create what the engineers wanted. So we've got a few constraints in there. What sort of constraints do we have? Well, in the motorsport world, we're a low volume manufacturer. So we can't actually go and get people to develop materials for us, unfortunately, because we have like 50 parts, we make 80 engines a year maximum. So nobody's going to actually develop engine materials for us. So we are restricted to use whatever's available. So we quite often are using what's available from aerospace, from automotive, but also the FIA technical regulations. That's one of the biggest things that is our restrictive constraints. And they require us to be able to make sure that anything that we use, all manufacturers are available as well. So anything that Ferrari use, we should be able to get hold of as well. Same with vice versa. So we can't actually create our own processes and sort of squirrel it away. It's deemed unfair, apparently. So yeah, we're not allowed to do that. And we've got restrictions on the actual materials we'd like to use. So we'd like to use things like metal matrix composites and things like magnesiums, but the FIA regulations restrict what we can use. But on the other side, there are also some grey areas where you can sometimes exploit the rules. So that's one of the fun sides of the job as well. But the biggest thing, the biggest constraint that we have is time. When the red lights go out, if you're ready or not, you've got to be ready, essentially. So at Mercedes, time constraints drive everything that we do. The issues that we have generally trying to get applications and processes ready. So quite often an engineer will require us to be able to come up with an idea, and it's whether it's been driven from a failure investigation or driven from something that they've developed. We have to be able to act fast to be able to provide a very robust application process. So whether it's a new forging or whether it's a coating, we have to make sure that it is applied robustly. Sometimes we have to do bespoke testing. We have to get a little bit innovative. We're not allowed to, well, sometimes we just don't have the time to be able to go and get some tensile specimens made out of a component or anything like that. So whether it's just a hardness check, something very rudimental. Yeah, we've made 3-point bend tests out of tiny little specimens just to try and understand the strain rate of the strain of a nickel plating. So we can do all sorts of different tests. I mean, speed is always the element there that you've got to get the results as quickly as possible. But of course, concise communication, got to be flexible as well. So whatever your time constraints you think you may have, quite often they'll change. They're always got a new, better idea, or something's going to change to improve, and you've got to get there before the red lights go out. So that's a bit about materials engineering at Mercedes. I like to think that the role is always split down into four main points, four key sort of application processes that we're involved in. So we got the development side of things. We add detail at the development process. So the engineers define the concept, and we provide the whatever materials or whatever processes we think fit the bill to get their concept working the best. And this time can vary anywhere between 1 week or 6 months. It depends what the issues are. The sort of materials that we quite often use, though, are things like aerospace alloys. We're very fortunate in the fact that we can get hold of aerospace grade nickel alloys or titanium aluminides, and we can use these sorts of materials. So as a materials engineer, it's an absolute dream to be able to play about with some of these more innovative materials. We use things like performance polymers. PEEK is something we regularly use. Things like that, polyimides, elastomers, and we use some composites as well. We also have access to all the different processes. So anything like additive layer manufacturing, things like physical vapor deposition, DLC coatings. We apply whatever's required to be able to make the component live in the very harsh environments that is Formula One. We have to do all this with the restriction of the FIA regulations. Say articles 5.16 to 5.20. Those are really our Bible. That tells us what we can and can't use. Materials characterization. So I touched on that earlier. But this is where materials engineering, we're once again adding the detail. We've got very low factors of safety within the motorsport world. So the reason for the low factors of safety, fairly obviously, is performance. We have to make sure that essentially we don't have too much excess material. We want to cut it down as much as possible. That's the only way you're going to win. So if you've got such low safety factors, you've got to get very accurate. And I think this is one of the key parts where materials engineers make a big difference, is that we make sure that we have very accurate material properties. So whenever we're doing any characterization, we make sure we've got the material processes involved. I mean, if you think about where do we get properties from, I mean, you can try Googling it. I'm not sure if you're going to get the properties of nickel alloys at 800 degrees. That sort of thing just doesn't really exist. And even if you could find it, you might be able to find it, but would you trust it? Do you know anything about the data analysis that's gone behind it, the material that it's got there? You can't, you can't obviously do those sorts of things. So at Mercedes, we have a very highly developed methodology that the engineers trust. So we all our data, all our processes that we use, and all the materials that we use have been captured and characterized by ourselves. And the key part is that we make sure that we've got the manufacturing processes involved. So whenever we're doing a material characterization, we make sure that we are not just doing the material with the right heat treatment, we make sure we've got the right surface finish. We make sure we've got the shot peening effect on there. We make sure we've got the coating that's actually going to be applied on there. Because when you're working with factor safeties of about 1.2, you can't afford to be anywhere slightly off. So we've got to make sure that we replicate absolutely everything that the component is going to be in there, so that the engineers can put it into their analysis. Once again, as I said before, sometimes we do our own bespoke testing. Depends what we need to do. If we can't find an off-the-shelf test, then we'll do our own test to make sure whether it's sort of we're testing the wear of an abradable coating or something along that lines. We'll create our own tests to be able to generate our own data. But it's this detailed characterization that really gives our engineers the confidence, so they can design with the down to the factors of safety that gets us the performance. And the third part of this is materials and processing controls. So having, as I said before, done all the hard work of doing the characterization, making sure you've got the right properties, the right surface finish, you've then got to actually make sure that when it comes to manufacturing the components, you are going to be getting what you've already measured the properties for. So we've got to make sure that we've got a detailed specification that has a very small window, a processing window. And this is the key to getting consistent properties. We don't like to have surprises, and we've got to make sure that we get the consistent properties from our supply chain or from our internal manufacturing. And we do that through detailed development of our supply chain. So the suppliers are actually developed. We have I suppose, a selection of supply chain specs of companies that we work with, and we treat them as like an extension of our team. They are all aware of what we're trying to do, and they're all brought on to having that same mentality of high quality. We've got to make sure the internal documentation captures the process envelope. As I said, it's absolutely crucial that we don't have a very wide manufacturing envelope for our parts. But also traceability. So traceability is a real key part, and that's really for things like failure investigations. We make sure that all our supply chain knows exactly to the serial number how they can trace back to the what they have manufactured and what is a heat treatment, what heat treatment process, things like that. There's some real detail that we go through, and that helps with our development feedback loop. So all the team members and suppliers, they all understand the consequences of any change to the process. So they know that if you've got any change in surface finish, residual stresses, microstructure, the properties are going to be very different to what you've measured. And then that means that the component is going to behave differently to what you're expecting. So a quick example of how we would do or complete a process development on a component, and how a materials engineer would fit into that is, let's example, an additive layer manufacturing metallic component. So the engineers would come to us and we'd talk through what it is that they're after, what sort of properties they need, and then we then look at our chosen supply list. We'd have 3 or 4 different suppliers we'd work with, and we'd select which one depending on various constraints of sort of material properties, how many volumes, how quickly they need it. So that would be the application process, the development process. Then obviously, if we don't have material properties, then we'd have to go away and measure the mechanical properties of the part. So we have to make sure that we've got the properties of the components that has, let's say, the exact powder size, the right powder, traceability of the right powder, and with whatever properties that's needed, we would be doing those tests, whether it's fatigue, thermal, whatever it is that the engineers need for finite element analysis. We'd always be making sure that we're putting into that, excuse me, the surface finish, for instance. We have to do a hot heat treatment, shock peening. We'd make sure that all that is put into the testing to make sure that our results are accurate. And then finally, the standards control sort of side of things, making sure the requirements capture exactly that process envelope. So we'd make sure the processing requirement window is as small as possible. And we also make sure that we've got an inspection criteria there, whether it's something like having a tensile test specimen made up with the components, and you can test each one to make sure you've got that feedback loop, whether you're doing NDT testing, like CT scans or something like that. We put all that detail into the specimen as well. So each step of the way, we'll be working with the engineers, making sure, taking their ideas. We're working with the manufacturers as well, manufacturing engineers and the supply chain. And we'd be, as a materials engineer, in the central hub, trying to capture all that data, trying to test the right data, generating the right data for the engineers, making sure that detail is all captured and the results are correct. And of course, there is the fourth element of what materials engineers do when it all goes unfortunately wrong. You may recognise this from a couple of races ago. It's like these that really ruin my Sunday, I can tell you. I know my week is going to be very bad when I see things like this. And George didn't look very happy either. But yes, failure investigation is a big part of what we do as a materials engineer as well. And when we see things like that, the engineers, they want to know three things. What's the failure mechanism? Has it failed by overload? Has it failed by fatigue? And where has it failed from? Has it been a manufacturing defect? Is it design? Is there a material defect in there? And does the material comply with the requirements? I've lost count the number of times that the first thing that people say is, "Oh, check the material. Is it the material's at fault?" It's generally, I think, 2% of the failures are ever actually a material fault, but it does happen. That is true. So a quick example of a failure investigation. So once again, I said materials engineers, we're there hopefully capturing the details. We're capturing things like the serial numbers, part numbers, getting low magnification images, making sure that everything is captured. And then we're going to be collaborating with the engineers, understanding what was going on with that particular powertrain before it went bang. So we're extremely fortunate, I must admit, that we've got sensors all over everywhere. So we know exactly what this engine was doing up to a millisecond before it went bang. So we quite often we're led in a certain direction of what has gone wrong. And we'll take a look at it underneath the microscope and do a bit of fractography. Unfortunately, I'm not particularly very good on that. But we've got a component here. We've got the fracture face is a large part of what you can see there. And then we've got the down the bottom left here. I'm not sure if anybody can see it. Got a right on the screen. Good on the screen. Okay. Well, that's a good thing then. Yeah, we've got the a fatigue initiation down the bottom there. You've got a telltale thumbnail down the bottom there. I was going to ask if anybody could see what it was, but I can barely see what it is, so that'd be a bit unfair. So we've done a bit of optical microscopy, looked underneath the microscope, and that's told us that yeah, the component has failed by fatigue. Then we can get a bit more detail. We take a look at it under the SEM, the scanning electron microscope, and that gives us a bit more detail. We have a look on the SEM, and we can see that it's not actually failed by at the surface. It's a subsurface initiation, which is looking like some sort of non-metallic inclusion. So we know that if it's not surface initiating, there's definitely some sort of issues there, and we've got a non-metallic inclusion there. But that's not really the end of the story, because we need more detail on that. We need to understand a bit more about what that could possibly be. So, as it's been identified, we can use the SEM again to get some chemical composition. So the EDX analysis, energy dispersive X-ray, that can identify what the difference between the general steel and the actual inclusion in there. So we can use that piece of information to try and understand a bit more about the source of that failure. So we can see on here we got some maps, and on these maps is showing you got high aluminium, silicon, and magnesium, as well as oxygen in there. So that's actually a fairly standard indigenous non-metallic inclusion. So it could have been that it was part of the steel making process. In fact, part of a refractory, the crucible or something like that. But in actual fact, it is a fairly standard inclusion that you can find in steels. So we've got to generally the detail of what's actually caused the failure. And at Mercedes, you then have a whole raft of activity then goes on. The quality department go into overdrive. They have to identify the location of all components with that material batch. So we've got further 8 engines out in the on the racetrack. Have they all got the same inclusion in here that could cause the failure? We have to find that sort of thing out. We go back to the suppliers, understand what processes they've been using to check. Is there anything different in there? And the engineers actually go and check the stresses were within design limits. So is this a one-off, or is it that all the steels actually have this in and they've got their calculations slightly wrong? And as a materials department, we go back and we actually check our properties. We have to make sure that any of our fracture surfaces, do they have that sort of size inclusion in there? If they do, that means that we've included that into our characterization. So therefore the numbers are right. If we haven't, then we'll have to look at re-evaluating. And the supplier will work with us as far as they can to try and remove some of these inclusions to the best of their ability. And the result will then be, do we change design because the stresses are too high? Do we change material requirements to make sure we've got other things in place to protect against these sorts of issues? Is that sort of feedback loop that we that materials engineering provides to get the detail into the failure investigation and feed back to the whole of the business. So this is simplistic view, but hopefully shows that materials engineers are in quite a few, every step, in fact, from the start to the end of the feedback loop. We're in there at concept review. We're there to add the detail to make sure that the application, we've got the right materials, we've got the right processes in place. We're there adding detail in the material characterization, making sure that you've got the detail there. At Mercedes, we're also there at manufacturing, making sure the controls are in place, to the specifications are there to make sure that we've got very accurate and very robust processes. And if we haven't done quite a good enough job as a team, we go to the engine test and it doesn't quite work, then we're in there in the failure investigation as well. And we go back around that failure investigation, add in the detail, go around that loop until we finally have some success. So really, in summary, say at Mercedes, we see the detail is essential. Maximum performance comes from small safety margins. When you've got the small safety margins, that requires real detailed engineering. And at Mercedes, materials engineers are there adding detail from concept to failure. from cradle to grave almost. And the detail feedback that we give to the designers and the manufacturing engineers all the way through that process, that's one of the key parts to keeping the I suppose the properties right, making sure the safety margins are low. And it's this close collaboration which helps us balance that fine line between maximum performance whilst avoiding failure. And I suppose the one thing I wanted to sort of take home from today is this doesn't just apply to Formula One. All industries are being driven to have improved efficiency, whether it's for environment reasons, whether it's to reduce costs. And whenever you're reducing your margin for error, you're maximizing performance, and vice versa. When you're maximizing performance, you're reducing your margin for error. And it's that detailed collaboration during all the processes between manufacturing, materials engineers, and engineering in general is necessary, because the performance is in the details. So that's all I've got to say today. So thank you very much for your attention. Do we have any questions?